In the second part of our electrochemistry chapter, there is a focus now on the use of electricity to extract metals. Okay, the previous one, the core material that we've just studied in terms of electrochemistry, was looking at how we could use electricity to bring about chemical reactions. All right, and that was explained in great detail. Now we're going to take a look at the opposite. How do chemical reactions bring about electricity? And that's a very important question. And it goes back to the very simple experiment that most of us probably did in primary school, where we had a lemon and we had a copper coin and we had a silver coin. Okay, and if we put them into the lemon and touched them off our tongue, we got the same zap as what we would get from probably a weak battery, which simply means that when you put your tongue between the copper and the silver coins, electrons are flowing. So there's a complete circuit. Now, do we have everything in place? The lemon is the electrolyte, the lemon juice, and then you've got the two metals, one of copper, say, and one of zinc. Because of the fact that these two metals are in different positions on the activity series, they have the ability to transfer electrons down that series. So if you have copper and zinc, poor spelling can mean absolute zero. You meet zinc before you meet copper, which means copper will transfer electrons to zinc through your tongue. So you'll get that zap of a current, and your tongue muscles will respond to it by twitching, because they'll feel that kind of zap of electricity. But we want to take a look and see, is the activity series enough? Or is there something else that we've got to do to try and measure how metals work in terms of a simple cell? And the answer is no, the activity series is not enough, because that's just a measure of how they react. Yeah, potassium the most reactive, gold the least reactive. But there is another series, which we call the electrochemical series, which is a way that we list metals according to their push. Now what I mean is according to the strength with which they push electrons from themselves into a circuit that they are connected to. Okay, and in this situation, again, potassium comes out on top and gold comes out at the bottom. But in order to try and get the metals into the electrochemical series, we have to tweak the procedure a little bit as to how we're going to measure this. But I want to just go back in history just very quickly to two very important people, Galvani and Volta. Now, we have a galvanometer in the lab which measures the flow of current, or shows us the flow of current. We have obviously the voltammeter, which shows us the voltage or the potential difference between the anode and the cathode, named in honour of these two particular scientists who dedicated quite an amount of their study to the phenomenon of electricity, as did Faraday, of course, as did Humphrey Davy. These are two people from the chemistry world that we have to tip our hats to and understand the importance of what they did. But the electrochemical series looks at the opposite of what we've just studied in the previous section. It looks at how chemical reactions are used to bring about an electrical current. Okay, and in particular, if we take Galvani's experience, he experienced that when he took the legs of a frog and he dissected out the nerves and made them visible, if he was to touch those nerves with different metals, the nerves contracted. The frog's legs began to move. Okay, so he discovered, for all intents and purposes, the mystery of animation of the muscle, the mystery of the animation of the living organism. And he thought it was electricity, and it is electricity. It's electrical impulses through what we would call our central nervous system and our peripheral nervous system. Okay, but he was the first one to show that different metals would bring about a contraction of muscles. Metals, chemical reactions, bringing about an electrical current which caused the muscles to tweak. Now, if you want to take a look at two videos, very, very interesting videos. One involves dissected frogs' legs being salted, and the other one involves squid tentacles being covered in soy sauce. Okay, keep in mind that these are cut off from the brain. Okay, so they have basically the nerves that were present in the legs, or the nerves that are present in the tentacles, but there's no brain present here. All that's present is a sprinkling of sodium metal. And the sodium metal, as we do know from biology, sodium is used in the transmission of nerve impulses, but the presence of that metal brings about a reaction in the muscular tissue which involves contraction. You can look at them yourselves. So, Alessandro Volta, then taking up the work of Galvani, was able to show that electricity is produced whenever two different metals are placed into an electrolyte. That's the lemon and then the strip of copper and the strip of zinc. Okay, so he was able to show that if you took copper and zinc and you put paper between them that was soaked in acid. So copper, paper, zinc, paper, copper, paper, zinc. You ended up getting a fairly big smelly apparatus, but an apparatus that actually gave quite a current and was able to produce quite a flow of electrons. So that's why Volta was honoured with the name volts. Volts were named after him. So volts are the actual potential difference between the electrode and the cathode. So in that particular cell that he worked with, what he did was he worked with zinc and he worked with copper. Now, this is what we call a half cell. And this one here is a half cell. Both of these operating together. This is a full galvanic cell. Okay? But it's made up of two half cells. And the reason why they can act as a full cell is obviously because of the salt bridge. Now, what does a salt bridge do? The salt bridge simply allows the flow of ions from one place to another. It allows the ions to move freely between the two solutions, meaning that in essence the two solutions are acting as one electrolyte, and therefore the zinc and the copper are joined in a complete circuit. What we do know, if you go through the activity series again, poor spelling can mean absolute zero. There's zinc. So we meet zinc before we meet copper, because copper's way down in leaving honours chemistry. There's copper. So zinc is above copper, which means that zinc is going to send its electrons through the voltmeter and back down to copper. And that flow of electrons is registered here as a voltage. Okay, 1.1 volts between zinc and copper. But we've got a bit of a problem. These metals are in two different positions on the activity series. That 1.1 volts is as a result of joining the two together. But in what ratio do they share this 1.1 volts? So how much of this 1.1 volt is due to the push of copper? How much is due to the push of zinc? And the only way that we can answer that question is by studying one metal at a time with another half cell that has a value of 0. Okay, and that other half cell is a very special type of half cell which we call a hydrogen half cell, and we'll talk about that now in a second. The hydrogen half cell, you can see here, is a half cell that is made up of platinum with hydrogen gas, elemental hydrogen gas, being bubbled over it. Now, this has an electrode potential. I'll talk more about electrode potential in a moment, of 0. And because it has an electrode potential of 0, any voltage that is produced by it and another metal is totally due to the other metal. Okay, so when you join a hydrogen half cell to copper, do you notice now the voltage has dropped to 0.3, which simply means out of the 1.1 volts we had between zinc and copper, 0.3 of that was due to copper. Now, if you had 1.1 volts between zinc and copper, and 0.3 volts are due to copper, well then you can see straight away that 0.8 volts will be due to zinc. What does that mean? Zinc has a higher push on its electrons than copper does, which means zinc will be able to push its electrons down to copper. Now, that pushing of electrons is the electrode potential. Yeah, it's the strength of a piece of metal to push electrons from itself to another metal. So the way in which we measure it individually is we take a hydrogen half cell, which is nothing more than platinum. That's an inert electrode. We bubble hydrogen gas over it. That has an electrode potential of 0. We connect it then via two half cells and a salt bridge, which is in essence one full cell, to another metal. And any voltage produced is due totally to the metal that is connected to the hydrogen half cell. So when we went through all the metals, potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, mercury, silver and gold, here's what we noticed. It was almost identical to the activity series, but there was one small change. And the small change was in the second and third metals. In the activity series, poor spelling can mean potassium, sodium, calcium, magnesium. But when we measured the electrode potential, we notice that calcium has a greater push than sodium does. So in fact, the electrode potentials gave us a new series called the electrochemical series, which was poor can spelling mean potassium, calcium, sodium, magnesium. So there was a swap around of elements 2 and 3 on the activity series to give what we call the electrochemical series. Okay, So the reference cell chosen, as we said already, was the hydrogen half cell, which has a potential of 0. So the hydrogen half cell has a potential of 0. So therefore any voltage that we get up here is due totally to the metal that is attached to the hydrogen half cell. When we did that, we got the electrochemical series, and as it says down here, the electrochemical series is a list of elements in order of their standard electrode potentials, meaning the strength by which they're able to push electrons away from themselves down into a lower metal. Chemists then proceeded to hook up all the other half cells to the hydrogen cell and measure the voltages they created, and the result was the electrochemical series. Now, do you notice? Poor spelling can mean. That's the way it should be if it was the activity series. But we've got a change here. It's now potassium, calcium, sodium, magnesium, because calcium is able to push its electrons a little bit more strongly than sodium can, and that's the electrochemical series. But as we go down this list, the ability of these metals to push electrons away from themselves again decreases until we get to gold, which practically doesn't push its electrons away at all, hence the reason why it doesn't corrode. So by using the hydrogen half cell, the metals in the activity series give us a list of decreasing electrode potentials. But because there's a change of sodium to calcium, we get a new series which we call the electrochemical series. So just to recap very quickly, galvani, different metals produce a current, okay, frog's legs. Volta, different metals in an electrolyte produce a battery, they give a voltage. Davy then exploited this in order to separate out elements like sodium, potassium and calcium, which hadn't been seen before because they remain compounded either in the sea or in the earth, and he extracted them. And at this stage we got an explosion of new elements on the periodic table thanks to Davy's use of electrochemistry. Faraday then came up with a very simple rule which simply said the following: if you are doing an electrolysis on a subject, the amount of substances that you will get at the anode and the cathode is directly linked to the power of the current. Okay, so in other words, the stronger the current, the more product you're going to get. There's a direct relationship between current and product. There's a link down here at the bottom, shock and awe, the story of electricity, BBC, a wonderful production. Now it's over 2 hours long, and you're not in school, so therefore there's plenty of time to watch this thing. But I would ask you, take snippets. Go particularly to the part that talks about Galvani and Volta, and just see how Galvani and Volta used their knowledge of electricity and their discoveries in order to enhance our understanding of electricity. What I will say to you is this: Mary Shelley either saw a demonstration or she heard about it, about the frog's legs and the reanimation of dead material through electricity, and she had a dream where a new man was built from the severed remains of different people, and that this new body was reanimated by lightning. Ring any bells? Frankenstein. So Frankenstein was actually Mary Shelley's reaction to the news that Galvani and Volta were doing these experiments on dead organic matter. Okay, so as we said, the electrochemical series is a series of metals that are listed in order of decreasing electrode potential. Electrode potential, the strength by which they push electrons from themselves. And they drop down from potassium to gold with a swap around between calcium and sodium. Metals at the top of this list can feed electrons downwards to metals below it. And the flow of electrons therefore creates a current. Okay. Now, what's so important about this is the following. If you were to connect any metal with a metal below it, the higher metal will feed electrons to the lower one. And that is seen particularly in what we call displacement reactions. So say, for example, if we had a beaker of copper sulfate, okay, Cu and SO4. Now, CuSO4, when it's placed into solution, gives Cu2 plus ions and SO4 2 minus ions. The sulfate radical is very stable and therefore won't react. So we're going to take that out of there, which leaves me just then with a solution of Cu2 plus ions. Okay. If I take an iron nail, which is made of Fe atoms, and I look at the position of these two on the electrochemical series, what do you notice? Who's first? Well, poor spelling can't mean absolute zero in. So there's iron. Iron is higher than copper. So iron is going to feed electrons down to copper, and usually it's 2 electrons at a time. So iron is going to feed 2 electrons to copper. What's that going to do? Well, if copper picks up 2 electrons, it's going to become copper metal. Yeah, solid copper. But at the same time, if the iron is losing 2 electrons, it's going to become Fe2+. And Fe2+ is far more stable than Fe, which means the Fe2+ then will fall into solution. So here we have a swap round. The copper ions in solution, being lower in the electrochemical series, will be given 2 electrons from iron. They have no choice because they're lower down. So iron will push its electrons onto copper. Iron will become Fe2+ and fall into solution. Copper 2+, which is in solution, will reluctantly take the 2 electrons, become copper metal, and where does it go? It coats the surface of the nail. So it sticks to the surface of the nail like that, and we begin to see what was a lovely shiny grey metal becoming the lovely rich red-brown colour of copper. So this is what we call a displacement reaction, where there's a swap of the position of the ion and the element simply because of a transfer of electrons. Okay, now take a look at this. So metals at the top push electrons downwards, we know that, and if iron is placed into a solution of CuSO4 which contains copper ions, the iron will feed 2 electrons down to copper in order to stabilize itself as Fe2+. Now take a look at this. This is iron, Fe, in copper sulfate. If we leave it there long enough, what's going to happen? Well, look at the 2 reactions. Iron is going to feed 2 electrons into copper, so therefore iron will become Fe2+, which will go into solution. And the copper ions, which are in solution, will pick up those 2 electrons, because they're lower down in the electrochemical series, to become copper metal. So over time, what was Fe in CuSO4 will become Cu in FeSO4. The blue copper sulfate will turn into green iron sulfate, and the grey silvery iron will become a lovely reddish brown copper. And that is called a displacement reaction. So metals higher up will displace metals lower down when the lower metal is in solution. And again, there's a video there for you to see that process in terms of the copper sulfate and the iron atoms. Okay, what else does the electrochemical series do for us? Well, it gives us a nice idea as to how quickly elements will corrode. Okay, now what is corrosion? First of all, corrosion, for example, we all know one thing is iron rusts. Okay, but a general definition of corrosion is an undesirable process, any undesirable process where a metal is converted into one of its compounds. And I want you to think very carefully of beautiful shiny iron becoming iron oxide. Okay, iron, strong, silvery, metallic. Iron oxide, brown, powder with no strength whatsoever. So it's an undesirable process. We don't want that to happen. How do we prevent it then? Well, first of all, we've got to try and figure out, well, why does it occur? And usually the corrosion of metals that are higher up in the electrochemical series, they corrode because of atmospheric elements like oxygen and water. Now, if we focus on iron for a moment, there's what happens. What was lovely, shiny, metallic iron over time becomes brown, dull, and weak iron oxide, which means it loses its strength as it corrodes. So it's an undesirable process. It's an electrochemical process because the metals higher up are going to be able to lose their electrons far more quickly than ones down below. So the ones higher in the electrochemical series, they will actually corrode far more quickly than the ones below. Iron rusts, gold keeps its lovely shine and its lovely colour. Metals at the top, as we said, corrode quickly. Metals at the bottom are very unreactive. So just think of gold. Just think of the 2, potassium and gold. Okay, and I learned that lesson very, very well when I was working with potassium for the very first time in school. I remember thinking to myself that if I was able to rub off the layer of protective oil from the surface of the potassium, when it hits the water, it's going to give a very good reaction. But what I didn't realise was that if you take off the layer of oil around the potassium, you expose the potassium metal to the atmospheric oxygen, an undesirable process. In fact, it's so undesirable that the potassium bursts into flames straight away. So it actually burst into flames on my hand, and I will remember that for the rest of my life. Okay, so there's gold, lovely shiny gold, which very rarely corrodes, and if it does, it's over hundreds of thousands of years. So let's just focus on iron. The corrosion of iron is a 3-step process. Number 1, iron being a metal will give away 2 electrons, okay? And when it does, it goes from this nice shiny metal here into this horrible dull grey, or dull brown, I should say, powder. Iron gives away 2 electrons. Now, what's in the atmosphere that reacts with iron? Water and oxygen. These 2 are floating around the place, okay? So when iron gives 2 electrons, the first thing that happens is that these 2 electrons are taken up by both the oxygen and the water. And that gives me then an abundance of hydroxyl ions. Do you see that? So now, if you're forming hydroxyl ions from the 2 electrons reacting with the oxygen and the water, these hydroxyl ions then will be attracted to the positive iron, which is produced as a result of losing 2 electrons, to form iron hydroxide. And the iron hydroxide then, as we know, is that brown, horrible thing that we call rust that falls away and actually eats away at the body of a car or anything else that's made of iron. So how do we prevent it? You've done this in your junior cert already. If I had a bar of iron, yeah, there's a number of ways I could actually prevent any corrosion. Number 1 simply would be to paint it. What does the paint do? It puts a layer of separation between the metal and the atmospheric elements. So the oxygen and the water can't get in. The iron can't give out its 2 electrons, therefore corrosion is stopped. But paint peels very quickly over time, so therefore it's a temporary measure. Okay, we can oil it. Again, the oil puts a layer of protection between the metal and the atmospheric elements, which means that there won't be any room for iron to give away its electrons, nor will be any chance for a chemical reaction to take place between the water and the oxygen. We can galvanize it, and we can electroplate it, and we can take a metal and turn it into one of its alloys. Now, of the ones that we have, the 3 I want to look at are these 3. Because there's a big difference between galvanizing and electroplating, and here it is. Galvanizing is exactly the same procedure as you taking your finger and putting it into hot wax. What happens? You get a lovely coating of wax over your finger, but you can peel it off, and again it allows the surface of the skin to be seen, so it's very easy to peel off the wax. Electroplating on the other side is where we bring about a chemical reaction to chemically bond one metal onto the surface of another so that you can't peel it away. And the biggest difference here is if you have a galvanized metal. Now normally iron is galvanized with zinc, okay? But if you scratch it, what happens is you peel off a bit of the zinc layer, the water and the oxygen get in, the iron is able to give its electrons, and underneath rust begins to happen. And it starts to spread, and eventually layers and layers of zinc will fall off, the rust will begin to spread more and more, and the rusting process again happens. So painting, greasing and galvanizing, they're all temporary. But electroplating and alloying are permanent, for the very simple reason that when we electroplate, we take a bar of iron and we chemically bond a layer of another metal like zinc over the top, so that even if there's a scratch, it's only that part there that will corrode. The corrosion doesn't spread because the layer of zinc can't peel away. It's chemically and electronically bonded to the outside of the iron. Alloying, as you know, is where you take metal 1 in molten form, add it to metal 2 in molten form to give metal 3. And metal number 3 has new properties, most of which are anti-corrosion properties, which is great. So I think an example would be copper and tin, as far as I know, SN, and that gives you brass. I think so. I think that's an alloy. But anyway, brass is not copper or tin. It is its own metal with its own properties. But keep in mind, it's still only a mixture. Okay, there's no actual chemical bonding between the copper and the tin. There's only a physical mixture between the copper and the tin in molten form. So when it cools down, it gives you a third metal, which we call brass, which has anti-corrosion properties. Okay. Paint. Let me just take these off. So we can paint, we can oil, or we can alloy. And alloying is usually made in wheels. Now, what gives the strength to the wheel is chromium, or, believe it or not, carbon. So if we add a pinch of chromium or carbon into another metal, it'll strengthen it and it'll give it anti-corrosion properties. Aluminium is a most unusual metal, all right, for the very simple reason that aluminium builds in its own anti-corrosion measures. Now what I mean by that is when you take a block of aluminium and you expose aluminium to the atmospheric elements, what happens is a layer of aluminium oxide builds up around the outside. But the aluminium oxide becomes very well bonded to the outside of the aluminium, like that. It bonds very, very tightly to the outside, forming a barrier between the atmospheric elements and the aluminium itself. So by the time it builds up a layer of corrosion, it doesn't fall off like rust. It bonds to the surface of the aluminium and it forms its own barrier against further corrosion. So whilst it corrodes initially, the corrosion comes to a standstill because the aluminium oxide, Al2O3, on the surface of the aluminium actually forms its own barrier between the metal and the atmospheric elements, forming no further corrosion. So it actually stops its own corrosion. That's why it's used on airplanes, and it's used as in shipbuilding, and usually in metals where we don't want corrosion to take place. Windows and houses have it as well. So when they're exposed freshly, a layer of aluminium oxide builds up, but it sticks and prevents further corrosion. So in fact, corrosion in this case is a good procedure for the aluminium metal itself. There's the aluminium oxide there, so Al2O3, and there's the aluminium. So when the oxygen tries to get in, it can't. When the water tries to get in, it can't. So they bounce off and there's no further corrosion, so the aluminium is self-protected. Okay, so as I said already, airplanes, boats, things that have long distances to travel and we want to use up small amounts of fuel, the lighter the objects, the better. That's why aluminium is seen as such a good metal. Stainless steel is another example of where we can prevent corrosion through alloying. So when you take steel and you mix it, and steel, by the way, is a form of iron, yeah? When you mix it with carbon or you mix it with chromium, you get an alloy. And that alloy is what we call stainless steel. If you look at your cutlery, sometimes you notice printed on stainless steel. What does it mean? It's not going to corrode. It's not going to tarnish. It keeps its nice luster. So it's steel, which is a special form of iron, reacting with carbon and chromium in the alloy as a physical mixture, giving you a new metal, which we call stainless steel, which again doesn't have any, which doesn't corrode, which doesn't have any corrosion properties. It's anti-corrosion. There they are. There's your elements there, cooking utensils. And the chromium, as we said already, forms a layer of chromium oxide which protects the steel from further corrosion. The last thing I want to look at is what I think called sacrificial anodizing. Now, as the name suggests, anodizing, what does an anode do? An anode gives away electrons. Okay, so say for example you have a block of iron. Under normal circumstances, if that's exposed to oxygen and to water, what will it do? It'll feed out 2 electrons. Then these 3 will give rise to hydroxyl ions, which will go back and attack the Fe2+, which will then form FeOH2, which is rust. Okay, now we don't want that to happen. So therefore, what do we do instead? We take a block of iron, and onto it we stick a block of something like aluminium. Okay, so there's your Fe and there's your aluminium. Now, what happens in this case? Well, iron tries to give away 2 electrons, which are immediately replaced by the aluminium. Why? Because aluminium is further up on the electrochemical series. Poor can spelling mean absolute. 0 in. So aluminium is 2 steps above iron on the electrochemical series. So therefore aluminium, every time iron tries to lose electrons and corrode, aluminium will replace them. So therefore what happens over time is the aluminium begins to wear away and the iron remains corrosion free. So where does this come in? Sacrificial, why? Because the aluminium is corroding in place of the iron. The aluminium is sacrificed to prevent corrosion on iron. Where's the anode? The aluminium is the anode because the aluminium is giving the electrons to iron and preventing iron from corroding. So instead of the iron corroding, the aluminium corrodes. And again, where do we see this? We'd see this particularly on the bottom of ships. Okay, there. So there's the propeller, there's the main body of the ship, and there's the fin that gets the ship to turn. Now you'll notice here that there's a block of aluminium. So what happens is the iron tries to lose 2 electrons, but the aluminium immediately replaces them. So as the iron tries to corrode, it can't. It loses 2 electrons, the aluminium pumps them straight back in again. But as the aluminium loses electrons, there's nothing there to replace the electrons for aluminium. So over time, as you can see from this, the aluminium corrodes away and the iron remains corrosion free. Now the one thing we do have to remember is that the aluminium blocks have to be replaced from time to time because of the fact that they corrode. If we didn't replace them, then as soon as they wear out, the iron would start to corrode, so they have to be replaced quite frequently, and on main and such as one part of the ship, they're all over the bottom of it to make sure that the iron remains corrosion free. Another place this works on is in relation to pipes. If your pipe is made of iron, normally they should just simply corrode. They should give their 2 electrons to the atmosphere like that, and they should corrode. However, if you attach the metal iron pipe to a bag of scrap aluminium, what will happen is, as the iron tries to lose 2 electrons, the aluminium then will feed 2 electrons in here and replace them. So as the iron tries to corrode, it's not able to, because as soon as it loses electrons, they are replaced from the aluminium, meaning that the aluminium corrodes and the iron remains corrosion free. So that's a lovely way to exploit the electrochemical series. Unfortunately, for the demise of one metal higher up in the electrochemical series, which prevents the corrosion of a metal which is lower down on the activity series. Okay, and that's what we have there. So the anode therefore corrodes instead of the iron. So it's called sacrificial anodizing because the aluminium is giving away electrons to iron, and as it does so, it is corroding, preventing the iron from corroding itself. So it's sacrificing itself to prevent corrosion in iron. That's why the electrochemical series is so important. So I'm going to stop there. The next section we're going to look at will be how we use electricity to actually separate metals out of either their molten form or out of their earthly ore, like bauxite or like hematite or ferrite and so on. So I'm going to stop there with that. And again, if you have any questions, please feel free to give me a shout.